Welcome to Week 10 for APSC 174. For the last 3 weeks of the course, we're going to be looking at invertible matrices and determinants, and then at the end we're going to be doing our capstone topic, which is eigenvalues and eigenvectors. Note that for these last 3 weeks we'll be using incomplete note sets, very similar to your calculus class. So I'd encourage you to download those in advance, the blank notes, and then that'll let you follow along, building up the notes as you go through following the videos. All right, let's get started. We'll begin by a quick review of linear functions and the various forms that we've seen them in so far. Let's start off with a vanilla presentation here. L of xy here has 3 components to it. So we're going to transform from a 2D function, input from R2, and we're going to have the output in R3, like so. And you can imagine plugging in specific values here and getting a 3-dimensional coordinate back, and that's all fine. And this all looks very linear. There's no constants at the end, so if we put in 0, we're going to get 0. All the other rules will apply for this linear transformation. What we see after a while of working with this kind of form, though, is that it doesn't give us a lot of insight into the space that we get back, into the subspaces, image, and all that. So what we can do is translate this into more vector and matrix forms. Let's do that quickly here. The first component of our new output can be written as 2x minus 3y. Well, we can write that out as 2x plus negative 3y's. The second component is 1x plus 1y. And the third component is 4x's plus 5y's. Note that this form is really handy for thinking about the image. The image in this case here of L will equal the span of, we can read it right off here, the span of the vectors 2, 1, 4 and negative 3, 1, 5. The span of those 2 vectors is going to be a plane in 3D, and those will be the only points we can reach with this linear transformation. But that's an advantage of this form over the sort of raw form up top. We're actually going to jump down to the bottom here. If we imagine x and y as a vector, then notice that we can keep all the numbers the same, the position the same. And if we did matrix multiplication with this form and the xy as a vector, we would be taking the top left multiplied by x and then the next one over to the y. This is the matrix multiplication operation moving from left to right here and down in the right-hand matrix. And we would get exactly this form here, which translates exactly back to the original form we started with. And what we find out after working with these enough times is that most of the information we're interested in is contained strictly in this matrix. So we associate with this linear transformation a matrix A, and this is our matrix for the standard form, or the standard matrix rather, for L. So in some sense, this matrix here encapsulates everything we know about the function up here. Okay, so that's different ways to represent a linear transformation. Here is a very specific concrete example. Let's look a little bit more at a general case. So if we have a linear map from one space to another, we had some nomenclature that went with that. The set of all input vectors that are mapped to the 0 value, the 0 vector in the output, is called the, think about it for a moment, hopefully yes, the kernel of L. I think of this as a squishing. So when you have a bunch of points in the input space, but they all get turned into zeros, that's sort of compressing one of the dimensions or one or more of the dimensions down to the 0 value in the output. And that's hopefully an association you're building in with kernel as you're getting more and more experience working with these. The complement in some sense to the kernel is the image, and we talked a bit about that in the last page. But the idea is that this is the set of values that we can reach. The set of y's in our output set, in the output, that is reachable by L of x. Let's put straight line for our vector notation here. L of x equals y for some x in the input space V. Now, just to illustrate as a hypothetical or as a concrete example here, in R3, imagining mapping from 3D to 3D with this transform L, let's draw it down here, we know for sure that the point 0 will map to the point 0 given any linear transform. That's one of our properties of linear transformations, or linear mappings. However, it may also be that there's a subspace, here we'll just draw it as a line, where all of these points get mapped to the 0 vector over here. And if that's the case, what ends up happening is, as we'll talk about in a second with the rank nullity stuff, we would be able to reach only a certain number of points, or a certain plane of points, in the image space. So all the other points that we have out here, they are going to map only down to this plane. So there we get a little bit of a distinction between the image of a function and the codomain. The image is the plane. The codomain is all the possible 3 dimensions we could have worked with. We just didn't end up needing them all for this particular transformation. So kernel is this green line in the input space, and the image is this red plane in the output space. And again, we can make this way more general, but it's nice to have some touchstones we can come back to. So just to emphasize that, both the kernel and the image are subspaces. The kernel is a subspace, so that closed under addition, scalar multiplication, all that. The key thing though is it's a subspace of the input space, whereas the image is a subspace of the output space. Now if we quickly sketch that out with our same 3D to 3D example, R3 to R3, if we have our 0 mapping to the 0 point, so again this is a mapping with our function L here, and if we had a whole line of points that all mapped, all of these mapped to the 0 point over here, and we had our image as some plane, that's our image of L, and this is our kernel of L, then because both of these are subspaces, we can talk about building blocks that would make them. Now that's easier to see in some sense on the image side here. We could imagine 2 vectors in this plane, and it can be any 2 vectors at all, but those 2 vectors, sorry, any 2 vectors in the plane that are linearly independent, those would be a basis for the image of L. Meanwhile, on the other side, this is a one-dimensional space, so let's use a contrasting color here. This vector, or any vector along that line, would be a basis for the kernel of L. And again, the basis idea is handy because it lets us distill this huge, infinite, 2-dimensional set of points down to a much smaller set of building blocks that can be used to recreate it. And likewise, once we know the direction of this one arrow, any one of those being a basis for the kernel, then we know the rest of the line. There's nothing hidden or mysterious about all the points in this line, as long as we know the direction. All right, so every linear transformation L has this kernel and an image. Notice the kernel can be really boring. The kernel could have just been the 0 point, mapping to the 0 point here. That's the 0-dimensional case for the kernel. But there's always a kernel, and there's always going to be an image. Now, because we also can map between a linear transformation and a matrix, we often talk about the kernel or the image of a matrix as if it were a linear transform. And that's basically what we're doing when we consider the matrix and imply that we're going to multiply it by some x's and y's, or the appropriate dimensionality of some vector. If we say this matrix has a kernel, what we're thinking is the matrix that represents a transform has a kernel. It's just way too complicated to say that every time. So transformations have kernels and images, and we can also then think of every matrix having a kernel and an image as well.